Hello folks! In this video I'm going to show you how I repurposed cells that I salvaged from warehouse robot batteries to build this battery for my custom electric motorcycle. I put a link to the playlist in the video description below in case you are interested in seeing more of that project, as well as links for the parts and materials that I used in this video. I'm using the QS273 hub motor rated for 12 kilowatts continuous and 24 kilowatts peak in the bike, so I designed the battery around the M50LT 21700 NCM lithium-ion cell, which is produced by LG specifically for light electric vehicles and is rated for 4.8 amp hours, 10.3 amps continuous, and 21.4 amps peak at 3.7 volts nominal. I'll be using them in a 16P20S configuration to provide a total 76.8 amp hours with 165 amps continuous and 342 amps peak at 74 volts to meet the demand from the motor and controller. To make it easier to handle when installing in the bike, I decided to split the battery into two 36-volt modules that will connect in series. Installing them in the bike with a gap between them will also help cool them better when I'm riding. The enclosure will be 3D printed with PETG filament using my new KD X-Max 3 printer, and the side panels will be engraved and cut from acrylic using my 22-watt Delta laser engraver. I might have to incorporate closed-loop forced air cooling in the modules later, depending on how hot the cells get during the initial test ride, so I designed the enclosures to allow for adding a couple of fans and a heat exchanger, and I incorporated channels around the perimeter of the enclosures to help lower the pressure and maximize airflow through the modules if I find the battery needs it. I purchased 3 of these 36-volt battery modules from batteryhookup.com, which contain the M50LT cells that I'm after. After testing them at around 1C, I found that even these used cells are still holding almost 100% of their rated capacity, which is a good indication that they still have lots of life left in them. They're also matched and balanced really well, but in order to make them work for my project, I need to tear the old modules down and rebuild them into the 16P20S configuration. Notice that I'm wearing rubber gloves for protection, and I wrapped electrical tape around all of the metal tools that I used to help prevent a short when I'm working on this. You can see the positive and negative connections are all exposed after removing the gray thermal pads, so I immediately covered them with tape as well. The original modules have a BMS built into them, but they can only handle around 30 or 40 amps at 36 volts, so I removed those and saved them for a future project. The bottom of the module has a sheet of plastic glued to it, and I found that heating it up to around 50 degrees Celsius made it a lot easier to peel off. Once the glue was cleaned off, I checked the voltage of each of the P groups to make sure they matched. The nickel strips were both welded and epoxied to the cells, but they were too thin to handle the current that the new configuration will provide, and cleaning all the glue and epoxy off to get a good connection for layering more strips over the originals seemed to be more work than they were worth, so I decided to remove the strips and bus bars completely and start from scratch. I removed the strips very carefully by using a small dull wood chisel to pry the strips away from the cells, and used the cell holder for leverage to avoid prying against the cell itself. Because these cells use NCM chemistry to provide a higher energy density than LFP, they're more unstable as a result, so they can burst into flames if they're punctured. When working with cells like this, it's best to keep a fireproof container and a fire extinguisher within arm's reach. After the strips were removed, the spot welds were still left behind, so I cleaned those up with a Dremel tool, again being very careful not to puncture the cell. Then I removed any remnants of the epoxy that might be left behind with some fine sandpaper. Two of the modules just needed the strips removed, but the third module also needed to be split in half, and each half combined with the other 2 whole modules, so I worked on that next. Once the modules were combined, I could start reconnecting these cells using 8mm wide by 0.2mm thick pure nickel strips and my new kWeld spot welder. This material can only handle around 7 amps continuously, so I'm using 2 layers to connect the 16 cells in each column of the modules in parallel first. This will allow the full rated cell current to flow with little resistance between each cell when they equalize as a parallel group and act as one larger cell. After the cells in each column were connected in parallel, I then connected the P groups in series, again using 2 layers of 8mm by 0.2mm nickel strips at each cell location. This ensures that each cell can safely transfer the full rated current to the adjacent cell in the next P group. With 16 double-layered strips forming the series connections between each P group, and with each double strip handling 14 amps continuous, the series connections can handle a total of 224 amps continuous, which is around 25% more than the continuous current rating for the motor. Once the nickel strips were connected, I covered them with vinyl and soldered 20-gauge balance wires to the top of each series connection between the P groups. These will be connected to the BMS later, which will use them to monitor the voltage of each P group during use to provide some protection against overcharging or over-discharging, overcurrent, overvoltage, and undervoltage, as well as provide some passive balancing while it's charging. Generally, it's a good idea not to solder lithium cells because the heat could damage them, and usually when I do need to involve soldering, I'll solder the nickel strips before welding them on. But in this case, I got ahead of myself, and the balance wires can be placed anywhere on the series connections anyway, so I soldered them in the middle of the strips to keep the heat away from the cells. Next, I needed a way to connect the battery to the speed controller, so I drilled and bent some 1/8 by 3/4 inch copper busbar material to connect to the positive and negative sides of the modules using 14-gauge wire, ring connectors, and stainless steel machine screws at each cell location, similar to the nickel strips. The bus bars are sized to each handle around 25% more than the total continuous current demand from the motor, and the 14-gauge wire and ring connectors can handle the same 14 amp current as the double-layered nickel strips. I put some links to bus bar, wire, and battery strip ampacity charts in the video description below as well. After connecting the ring terminals, I placed a small amount of 5-minute epoxy around the base of the screws to help lock them to the bus bar and prevent them from vibrating loose over time, and it will help seal the connection from moisture. I then soldered the 14-gauge wires to a nickel strip so that the solder joint lands between each cell when the strip is welded to them later. The bus bar for the positive side of each module is a bit different from the negative side, with an extra bar that's bent to connect to the bottom of the other before returning to the top of the module. But this is for good reason. If the bus bars on each side were identical, then the current being pulled through the battery would choose the path of least resistance, which means it would flow directly through the cells in the top of the battery only, and the rest of the cells would trickle charge the top cells to equalize afterward, as shown in the picture. This would lead to the top cells being worked harder and degrading a lot faster than the rest, if it doesn't damage them completely from the start. To prevent that, the current needs to be pulled through the middle of the battery to share the load directly with more cells. And the best way to do that is to make it exit the battery at the opposite end that it started, as shown. This will help the cells to work more efficiently and degrade at a more similar rate so the battery lasts longer before it needs to be serviced or replaced. After the bars were connected, I placed a piece of ABS between the positive bars to keep them from touching and giving the current a shortcut to the top of the module. Then I wrapped them in vinyl tape as well. To help hold the bars in place when I'm connecting the cables for the controller later, I printed a vented PETG cap to fit over each module and secure the top of the bars. This will all be reinforced further by the enclosure. Next, I connected the modules together in series with a battery cable and connected the balance wires to the JST connector provided by the BMS manufacturer, and checked the voltage between each P group to make sure that I connected them in the right sequence and the voltages matched. The BMS that I'm using is a daily that's rated for 250 amps continuous, but it can be programmed to protect circuits with a lower current rating too. It has a built-in fan for cooling and also comes with Bluetooth so the user can connect to their app to view information about the condition of their battery or make changes to certain settings. The BMS is connected as shown and according to the sequence that daily details in their instructions that are provided with it. After the BMS was connected, I pressed the activation button on the Bluetooth dongle to wake it up, then opened the app on my smartphone to check that it's working. If the BMS is turned on, then a device name will appear on the first screen after opening the app. Clicking that will take you to the main screen, which gives you information about the state of charge, battery voltage, discharge and charge current, temperature, as well as individual cell voltage. You can see that the voltage difference between the cells is less than half a millivolt, so they're balanced really well. This page is also where error codes will appear if there's ever a problem, and right now it looks like everything is fine with the exception of the state of charge meter, which should be reading around 95% at 82.8 volts. But the meter won't ever be correct after it's first booted up because it depends on the battery specs which the user needs to set in the parameter settings. The first section under the parameter settings shows all of the default protection settings like overvoltage and undervoltage, overdischarging and overcharging, cell volt difference, etc. Normally these are already programmed for the type of battery that you're working with, provided that you ordered the correct BMS for it, but it's always a good idea to verify that these settings are all correct before using the battery. The next section allows you to set the amp hour rating for your battery, the nominal voltage of your cells, and when you want to trigger balancing. You can also change the state of charge meter here, which I'll do now to show you how, but it's best to do this after the battery's been cycled a few times, then charged and left to rest for 24 hours. After that, set the meter to 100% in the app, and it should keep track of how many kilowatt hours you use or put back into the battery, and compare that with the amp hour rating that you entered to match the state of charge meter accordingly. In order to save any settings that you change here, you need to click the Set button and enter a passcode. The default factory code is 123456. The next section covers information about how many strings and temperature sensors you're using. The section after that covers the temperature protection settings. And the last section allows you to enable or disable the charge and discharge switches manually, perform a factory reset, or change your password. With the modules assembled, it was time to start making the enclosures for them. So I imported the CAD for the top and bottom portions into the kWeld slicers to prep them for 3D printing. I used kWeld's presets for generic PETG filament, which has a speed range of 70 to 300 millimeters per second for different parts and layers. I then set the infill to 50% grid and clicked Slice to generate a G-code for it. After checking the layers, I exported the G-code to the printer and started printing. For a generic filament, the parts turned out pretty good. There were no issues with extrusion or speed. I did have to use a glue stick on the build plate to get the first layer to stick, but after that the parts stayed in place and didn't warp at all. The 50% infill seems plenty strong enough to support the 30-pound modules too. To make the side panels that will fasten to the center portions, I first started by exporting a high-resolution orthographic image of the panel face from SketchUp and opened it in Paint so that I could remove the background. Then I imported the image to Lightburn software, where I used the trace tool to trace the perimeter of the panel and mounting hole locations before deleting the original image. Then I used the measuring tool to help scale the traced image to the right size. The mounting holes that were traced ended up being slightly irregular, so I replaced them by using the array tool to create and position new holes. Once the geometry was done, I imported and positioned the graphics that I created that will fill what would otherwise be a blank space on the side of the battery. I incorporated a couple of logos, and the chip in the upper right corner seemed like a good place to put the battery specs. I set the cutting and engraving jobs in separate layers, so the cutting is done first, followed by the engraving. The settings that I use to cut are 250 mm per minute for speed at 100% power, and for engraving I use 10,000 mm per minute at 40% power and 0.08 mm intervals, with air assist turned on for both jobs. To make it more manageable, I cut a sheet of 3mm matte black acrylic to the approximate size that I needed on the table saw, before peeling off the protective film and placing it in the engraver work area. You can see that the Delta has some proper safety features built into it, like the kill switch and key switch, and it has air assist to improve engraving and cutting performance, which you can control manually with the external switch or automatically through software. It also has a built-in terminal display that allows you to do almost anything that you need to do without connecting the machine to a PC. After turning the engraver on, I double-check the layer settings in Lightburn, then click Preview to triple-check and get a rough estimate on how long the job will take, which was around 1 hour and 45 minutes to both cut and engrave the panel. Then I click the Frame button to position the workpiece before using the built-in focus stick to set the laser's focal point, and then start the cutting process. The panels turned out really nice. Some folks have asked if I'm worried about the acrylic cracking, but my only concern would be using flathead screws in the mounting holes because the holes would need to be tapered to match the profile of the screw head, and when the screw's tightened, it'll wedge itself into the acrylic and put pressure on the side of the hole. But I hope to avoid that problem by using round head screws that will just press the acrylic flat against the enclosure. With a short spacing of around 3 inches between each screw, they'll work together to make the enclosure solid while sharing the weight of the modules to prevent cracking. After the parts were all made, I started assembling. I connected the bottom piece to the lower side pieces off camera using kWeld at the joints along with screws. I then connected the upper portion of the sides to the lower portions with kWeld and 1/4-inch steel rods for reinforcement. Next, I installed the top portion and the connector for the balance wires. I'm just using screws to connect the top for now, just to show you folks how everything fits and what the modules will look like, because I still need to install a couple of thermistors in the modules which haven't been delivered yet, so I'll have to open them back up later to do that. But I'll be using black silicone to seal the top corner joints during the final assembly, so they can be taken apart for servicing later if needed without damaging them. After installing the connector for the balance wires, I turn the module on its side and fasten the acrylic panels. I'm just using nickel-plated wood screws to fasten everything, but I'm going to use flat black screws for the final assembly so they blend in better, as well as silicone gaskets between the panels and the enclosure to keep it watertight. I'm also going to paint the enclosure flat black inside and out to waterproof the PETG. But that's it for this video, folks. If you enjoyed it, let me know with a thumbs up or a comment. And make sure you're subscribed to the channel, because in the next video, I'm going to fit the battery and other electrical components into the bike and wire it up for a quick test ride to check that everything is working properly. I'm particularly curious about how the suspension is going to work, specifically the girder forks that I made. Until then, thanks for watching and take care, folks.